Hello, my name is Chad Husting. This is chemistry, and hopefully we're going to be looking at empirical and molecular formulas. So, what exactly is an empirical and molecular formula? Well, how are these the same and how are these different? So let's go ahead and see if we can take a look there. Okay, first of all, when we look at these right here, we notice that some of them are very similar, some of them are a little bit different. The way that we tell them apart is that if you have an empirical formula, these are formulas with the lowest whole number ratios. Whereas if you have a molecular formula, these tend to be formulas in which the ratios may be reduced to a lower ratio. So as an example, if I were to try to find the molecular formulas, H2O2 could be reduced from 2 to 2 to 1 to 1. That would be a molecular formula. C6H6, same thing. This could be reduced down to 1 to 1. This would be molecular. Molecular. CH2O1. This can't be reduced down anymore. This would be an empirical. Sucrose or fructose. This would be molecular. Water. Definitely empirical. So typically our job then is to say, given the data, how in the world would we even begin to calculate these? And typically, I got this from Mr. Geyer. This is what I think is the best way in the world to do it. Learn this poem, stop the video, write this down. And that is percent to mass, mass to mole, divide by smallest, multiply to whole. Okay, so what does this mean? Well, typically what this means is that whenever they're given any kind of compound, they put it inside a big chamber and they just heat the bejeebers out of it. I don't think that's a technical term, but I think you get the idea. And when they do it, things break down. And what they can figure out, oh, and by the way, this is the online book, which is actually pretty good. So here's some typical data you would get. A compound of iron and oxygen is analyzed. They blow it apart. They've got almost 70% iron, 30% oxygen. How would we find the empirical formula? Step number 1 of the poem says to do this. Percent to mass. So I can use any amount that I want. It'll always work. Let's use 100 grams, which is the same as 100%. So all I did was to take the percent of the percent of iron. Sorry, I just take the percent of iron and convert that. Just put a gram where it says percent sign, and then you take a percent of the oxygen, 30.6%, and let's make that grams. So we're just saying it's percent. Let's put it in grams. The next part of the poem says mass to mole. And that means, essentially, I'm going to take now what I have. I went from percent to mass. I go from mass to mole. So if this is 69.94 grams of iron through factor labeling, I find the moles of iron based on the atomic mass of iron on the periodic table. Here's oxygen, grams of oxygen. I go to convert to moles of oxygen. So this would tell me for this substance, based on the percentages that they gave me, the mole ratio that I have of moles of iron to moles of oxygen in of this substance. Now, next part, divide by smallest. To divide by smallest, I just take whichever moles. There's 1.252 moles of iron, 1.879 moles of oxygen. The 1.252 is smaller. I just divide by that number for both of them. 1.252 moles of iron divided by 1.252 gives me 1 mole of iron. This would give me 1.5 moles of oxygen. So the problem is, if I were to write this, it would look like FeO 1.5. We cannot have fractions for subscripts. So this is the last part of the poem. Last part of the poem says multiply to whole. If I have 1 to 1.5, I have to ask myself, well, what could I multiply to get a whole number? Well, it's easy, right? 2. So I multiply everything by 2. So now I've got 2 to 3. So this is basically iron 3 oxide, Fe2O3. Now, here's the really cool part. If you work backwards and you do a percent comp problem and you say, hey, let's, what's the percentage of iron in Fe2O3? Guess what you'll get? And it's going to be about 70%. So this is extremely handy. Okay, now let's do part 2. And for part 2, what if they say, hey, this is how you find the empirical formula, but what about the molecular formula? What if it's more? What if it's a higher ratio down here? Like, what if it's some compound where it could be like Fe4 to O6, even though that doesn't exist? How do we find that? Well, we need a little more information. You're just going to add one more step. So let's look. Okay, so here's an example. So in this example, it says the molar mass of a compound, 90 grams per mole. Analyze sample indicates so many grams of nitrogen and oxygen. So we don't even, instead of starting with the percentages, they're just going to give us the grams of nitrogen and oxygen. So we don't even need to do percent. Find the molecular formula. Now, whenever you do these, step number 1, find the empirical first. And that's what I did. How did I find the empirical? Well, percent to mass, it's in mass already, so I don't have to worry about that. Mass to mole. If you take 0.606 grams and get it to moles of nitrogen, 1.390 grams of oxygen, get it to moles of oxygen, I divide by smallest, it's a 1 to 2 ratio. This is the empirical formula for this information. Okay, so find the empirical first. Now, if I add this up, here's what happens. Okay, I found the empirical for nitrogen dioxide. It has a molar mass of 46 grams per mole. They're telling me that the molar mass of this compound for the molecule has to be 92. Okay, so it has to be like 92. So I said, well, okay, if that's the case, the molecular mass that they have to give you divided by the empirical molar mass that we were able to find. So we found the empirical, you add it all up, you take 92 divided by 46, you get a multiple of 2, right? So again, 96 grams per mole divided by 46 grams per mole. And it doesn't always come out perfect. Actually, wait a minute. This is wrong. 2. But it doesn't always come out perfect, but it's pretty close. Okay, so we divide these two, we get a multiple of 2. So watch what happens. If I take NO2 and I times everything by 2, I now get N2O4. Okay, now here's the cool part. It still has the right percent comp. It still gives me, this would be the molecular formula. And it would still, if I go back and I do the percentage of percent of nitrogen and I multiply it times the total of this, I get the exact numbers, so it still works. So basically, hopefully what you've learned is for the empirical, we go percent to mass, mass to mole, divide by smallest, multiply the whole. That will get us the empirical. To get us the molecular formula, find the empirical first. You want to divide the molecular molar mass divided by the empirical. Use that whole number to multiply the subscripts to get the molecular formula. Take time to go back and take notes, but these steps work 99.999% of the time.